next problem that I'm going to look at. And so this is our classic ramp question where we have a pulley and we have M1 is hanging and M2 is on the ramp. I give you the angle of the ramp, I give you M2, and I give you the coefficient of friction. And in this case, we have to decide what are the min and maxes that M1 can be such that the system will remain at rest. So this is me kind of walking through it up here. It says that if M1 is big enough, then it will accelerate down. Thus, M2 will go up the ramp. Basically, it'll overcome the weight of M2 down the ramp and the friction on M2, which is down the ramp. If M1 is small enough, then it will accelerate up because M2's weight down the ramp will overcome its friction and the weight of M1. And so we just have to, again, look at two different cases. So let's look at case number one where M1 accelerates down, which means M1's weight is big enough to overcome the other forces. So here's the free body diagram on M1, on M2. Tension's up the ramp, friction is down the ramp, the normal force is normal, which means it's perpendicular to the surface, so it's pointing up and left on the ramp, and M2G, of course, is down. I write the x hat and y hat equations for each. Same thing we always do. We look at this equation here and we find out that the normal force is m2g cosine theta. We substitute that in for friction because we know friction at its maximum is mu n. And we get this equation if we looked at just box on the ramp, box 2 on the ramp. Box 1 is easy because it's just tension versus m1g. And if we're assuming m1 is accelerating downwards, then go ahead and write m1g minus t equals m1a because m1g is bigger than tension if m1g is accelerating down. So you can take this t and you can throw it in for the other tension and then you get the system equation. You can do that algebraically, or you could have really skipped all of the steps and you could have just done that thought experiment or said, look at this system. What's making the system move? Well, the weight of m1g is driving the system. What's opposing it? Well, we have the friction on m2g, which is this term, and we have the weight of m2g down the ramp, which is that term. So if m1g is bigger than this combination, it will make this system accelerate. So I just solved for m1, and I get this. So if m1 is equal to that, then m1 will accelerate down the ramp. So I get 4.83. Anything bigger, now actually 4.83 makes the acceleration 0. Again, I'm right here, I say let a equal 0. 4.83 makes it 0. So if you have any more mass on M1, then M1 will accelerate down the ramp. Or excuse me, M1 will accelerate down. Okay, and M2 thus would go up the ramp. Okay, now let's look at case 2. Now M1 accelerates upwards, which means M1's not very big. It's the same free body diagram, except now if M1 accelerates up, M2 is then going down the ramp. So here, this frictional term, instead of being down the ramp, now it's up the ramp, because now M2 is going to slide down the ramp. Friction will thus point up, opposing the motion. So we get roughly these same equations, and we get the same system. So let's look at the system here, and it's kind of in this light green. Look at the system equation. m2g sine theta, the weight of m2 down the ramp, if that guy is bigger than the friction on m2 and the weight of m1, then the system will accelerate in that direction. And so I get a value for m1 and I get 3.83. Thus I have the range of masses. Look over here. Again, I found the min and the max. If m1 is bigger than 4.83, M1 will accelerate down. If M1 is less than 3.83, then M1 will accelerate up. And if you look at the equations, the only difference in the equations is the direction of friction, because friction in this case will oppose the motion of M2. If M2 is going up the ramp, friction will be down. If M2 is going down the ramp, friction will be up. And so you get this range at which it's stationary. Anything in between there, and M1 will not move. Well, M2 also will not move. If you're less than 3.83 or greater than 4.83, you're going to get an acceleration in one of the directions.